to consider linear momentum for today's lecture. Now, what is linear momentum? Linear momentum is given by the product of an object's mass and its velocity. The product of an object's mass and its velocity. Alright? So we can say that, and it's depicted by P. And we can say that P is equal to mv. Alright? Now, by definition, momentum is the measurement of a mass in motion. Now, any object with momentum is hard to stop. So if we have a mass which is moving at a given velocity, it is hard for it to stop, because the more the mass, the greater the mass or the greater the velocity, you realize that it will be hard to stop, because the momentum will also be what? Greater. Now, momentum is a vector quantity and it has a unit. It has a unit kilogram meter per second, or Newton second. Now, we said that momentum is given by mass times what? Velocity. Now, let's also look at impulse. When we talk about impulse of a body is the overall effect of a force acting on a body over time. Okay? It's the overall effect of a force acting on a body over time. It's also a vector quantity, and it is given by impulse is equal to force times the time taken. F is the force, and then T is the time taken. Alright. Now, I want us to take a few momentum examples. Let's take a few momentum examples. Alright, example 1. A body of mass 5 kilogram is acted upon by a force which changes the body from rest to a velocity of 6 meters per second for 5 seconds. Find A, the magnitude of the force and then B, the change in momentum. The magnitude of the force, and then B, the change in momentum. So I'll give you a minute to read through. I'll give you a minute to read through the question and think about it. Okay. So for our solution, we are going to use our second law of motion. Force is equal to mass times acceleration. And we will still first have to find the acceleration. We know the mass to be 5 kilos. We still have to find the acceleration. And we remember our V is equal to U plus AT. And if we make A the subject, it's going to be V minus U all over T. Now, when it says it starts from rest, that means that initial velocity is 0 meters per second to a velocity of 6 meters per second. And our time is given. Our time is 5 seconds. So let's find our acceleration. We're going to have 6 minus 0 over 5. What is 6 over? So our A will be 6 over 5 meters per second squared. We can also write it in decimal form, or 1.2, or 1.2 meters per second squared. Now let's use our second law of motion. Force is equal to mass, which is 5, times our 6 over 5. And we are going to have 6 Newton for the force that will act upon the body. Now we are to find the change in momentum. That's the second part. Alright? Now change in momentum, F of t, will be given by m into brackets v minus u. Now the mass is 5. Our final velocity is 6. Our initial is 0. And this will give us 5 times 6, which is what? 30 Newton seconds. And that is our answer. Alright, let's take another example. Example 2. A bullet of mass 0.4, mass 0.4 kilograms is traveling at a speed of 400 meters per second. Find the momentum. Find the momentum. This is very simple. We know that P is equal to mv, so our P will be 0.4 times 400. When we multiply 0.4 by 400, we are going to have 160. 160 kilogram meters per second. Yes. All right. Now I want us to move on to another principle. We'll take a couple more examples later. Or would you like a last example? Okay, let's take another example. Example 3. A force acts on a body. A force acts on a body of mass 0.5 kilograms, changing its speed from 3 meters per second to 7 meters per second. What is the change in momentum? Now our change in momentum is called impulse. Change in momentum is called impulse, and that is given by Ft is equal to mv minus u, or someone can write it as mv minus mu. Alright, now our v, that is our final velocity, will be 7 meters per second. Our u will be 3 meters per second. And so our f of t is going to be 0.5 times 7 minus 3, which will actually be 0.5 times 4. And what will this give us? This will give us 2 Newton seconds. 2 Newton seconds. Okay, you can try this on your own. Okay, you can try and solve this on your own. Alright, let's continue. Now, Newton's second law. What do we know? What do we remember about Newton's second law? I just quoted it. Newton's second law is force is equal to mass times acceleration. Okay? Now, we remember that acceleration is given by what? V minus u over t. Now, we can write it simply as change in velocity over change in time. Okay? Now, if we come and do a substitution of A in this force formula, F will now become mass times change in velocity over change in time. Okay? Now, if we try and multiply, we are going to get something like mv over change in time. Now, what is mv? Momentum. mv is momentum. So this is going to give us F is equal to change in momentum over change in time. So we can write our force as the change in momentum all over the change in time. Okay, now let's use this to solve a couple of questions. Changing momentum over changing time. Let's look at an example. Estimate the average force on a tennis ball as it is served. Served is when the player swings the rackets. The mass of the ball is 0.06 kilograms, and it leaves the racket with a speed of 40 meters per second. The contact time is 5 seconds. Alright, the contact time is 5 seconds. So how will we solve this question? We're going to use our force is equal to change in momentum over change in time. Okay? Now, we may have to find our momentum first. Now, we know that P is what? mv. So let's put it here. F will be change in mv over what? Change in time. Now, when we look at the change in mv, we look for mass, which is 0.06 kilos, and then our velocity is what? 40 meters per second. Okay, now it changes from 0 to 40. So at the end of the day, we'll have V minus U being what? 40 minus 0, which will still give us 40. Okay. And then we are told the time it takes is 5 seconds. That's a change in time. 5 seconds. So we can put everything here. Our force is now going to be 0.06. Let's remove the units. Times 40 all over 5. So we are going to have, let's all try and calculate it. Times 40 divided by 5. And our force is going to be 0.48 Newton. Okay. Okay. I'll look for more examples for you. You can also look through the book and then take some more examples. Now I want us to move on to the conservation of linear momentum. Conservation of linear momentum. This is a law. It's called the law of conservation of linear momentum. I think it's momentum. Yes. The law of conservation of linear momentum. This law is usually used to observe collisions. Okay, right. It's used to observe collisions. Now, there are two cases when there's a collision. Case one, if an object, let's say A, moving with its momentum, of course it will move with its momentum, collides with an object B, also moving with its momentum. The first case is that after collision, object A and object B come together as one body and then move. The second instance is if we have object A moving with its momentum, colliding with object B, also moving with its momentum. The second instance is that A, after collision, A and B separate and move as in different directions. Okay? Now, the law of conservation of linear momentum states that the moment before collision is equal to the moment after collision. The moment before collision and the moment after collision should be what? Equal. Now, before collision, we will have the moment maybe of object A. We can call it M. Before collision, we can call it MVA. MU, let's use U because that is the initial velocity. So MUA or MU1. Okay. Before collision, we have MU1 plus, now object B2 will be moving with its own, so let's call this M1U1 and then M2U2, that is object B. And after collision, we are going to have M1V1 plus M2V2. Okay, so they are saying that momentum before and the momentum after should be the same. And we are going to use this. This condition is if the two objects move separately. But if the two objects move together, and that there's a word called coalesce, they move together, that's a scenario 1. We are going to have M1U1 plus M2U2. At the beginning, they were not moving together, and this will be equal to M1 plus M2V. They will now move with one velocity. So these are the two conditions. These are the two conditions. The first one is for the object separating after collision. The second condition is when they coalesce. Now, if the objects are moving in opposite directions before collision, if the objects are moving in opposite directions as I depicted, we are going to have M1U1 minus M2U2 being equal to M1V1 plus M2V2. Okay? We are going to negate the second velocity. All right. Now, the last condition is if one of the bodies was at rest. Let's say this one was at rest. So if it's at rest, then u2 will be what? 0 meters per second or 0 kilometers per hour. So therefore, we are going to have m1 u1. Now, if we add plus m2 u2, this all this will be 0. So we'll take it out. And this will be equal to m1 v1 plus m2 v2. So let us take note of these conditions. Let us take note of these conditions. Okay? And we'll solve a couple of questions